Hey everybody, my name is John Herrikus and thanks for watching this presentation on cycle detection and cryptography. I'm going to try to keep this relatively straightforward and not go too deep into the math aspects of cryptography or my work because I know it's a very niche topic. But I will try to get use some nice visual stuff to get my points across, and hopefully you'll find this interesting. So here's a roadmap. I'm going to give a quick rundown of RSA and integer factorization, and then a real quick rundown of cellular automata and some demonstrations of it to put it into perspective. Afterwards, I'm going to jump into my work using this to factor integers. So most people probably know what RSA is, and I'm not going to go into too much detail here, but the least you need to know is that you have some integer n that is a product of two prime numbers. And associated with that, you have a public and a private exponent. Now, the RSA problem basically says finding the private exponent is hard. Now, there's what is called the RSA strong assumption. It is a conjecture that the RSA problem is intractable, although this isn't proven. Now, the RSA strong assumption implies that solving the RSA problem is as hard as finding the prime factorization of a number. This has not been proven either. This is an important distinction. Nor has integer factorization been proven to be intractable. That's not to say it probably isn't, but it hasn't been proven, and from a complexity theory point of view, it's very interesting. When it comes to factoring numbers, there are two methods I'll quickly mention, the first being the general number field sieve. Without going too deep, it looks for coefficients of a polynomial which map to zero across multiple domains. Conceptually, my work turned out very much in line with this, so I think if I can get my work across, you'll probably be able to better understand how the general number field sieve works. The second algorithm is Shor's quantum factoring algorithm. Now, this is the only algorithm known to run in polynomial time in factoring integers, and the way it works, more or less, is you evaluate a function at all points and find its period using the quantum Fourier transform. And the reason I mention it is because it actually gave me the idea of using a diagonal basis measurement in this work. You'll see what I mean in a little bit. So, what is cellular automata? Well, it is very, very simple. By that I mean you have a cell and you have some rules on how it's going to behave. So if you look up here, and you have a bunch of rules telling the automata how the next state is going to evolve. And you see, so if there's, in the first one, this is three cells mapped to 0, 2 cells mapped to 0, etc., etc. I'll give you guys a quick demonstration in Golly, which is a great program here. So we start with a bunch of cells arranged, saying, okay, and we iterate, and all of a sudden this information seems to be lost in noise. Or is it? It looks like we have, it's making a resurgence. And let's see if that's the case. And here we go, we're back to a self-similar tiling of the initial state. And now what happens when I just add a little bit of noise into this? Well, most of it's going to get lost forever. Maybe not now. Oh, this program is hard. Not right away, but eventually it's just going back to too much interference. So that's basically, this is how it works. It's very simple. So you can't talk about crypto and cellular automata without mentioning Stephen Wolfram and Rule 30. Wolfram, you may know, is the founder of Wolfram Mathematica. He studied Rule 30 extensively and even put it into Mathematica as a random number generator. He's also one of the first people to research encryption using cellular automata. You might also know his book, A New Kind of Science, which is like 2,000 pages long, and it makes you wonder if he is a madman or a genius. Here's Rule 30 after 1,000 iterations, and a couple of years ago, Wolfram actually created the Rule 30 prizes, which pay out if you can answer certain questions about the randomness of this structure, of whether or not it's ever periodic. So before I dive into my work, I'm going to explain modular addition very quickly in case you're not familiar with it. Formally speaking, k mod n is the remainder from dividing by n. So if the remainder is 0, then k is a multiple of n. You actually already know this concept from clocks, which operates in addition mod 12. So if the time is 5 o'clock 24 hours from now, I know that the time is also going to be 5 o'clock. Similarly, 13 hours from now, 13 mod 12 is 1, so I know it's going to be 6 o'clock. And that's basically what addition mod n is. I guess I'll point out too, I also use interchangeably reduce mod n, just so there's no confusion on that. So, now on to my work attacking encryption. So I've got a cellular automata with a very simple rule set. I take the sum of the neighboring cells and reduce it mod n. If I see the cells go to 0, then I know the sum of its neighbors were a multiple of n. So there's a bit more that goes into this, but I'm gonna hold off for now. What's so great about this? I mean, first off, it's extremely simple, both in terms of implementation, understanding, and computational complexity. And we use a pre-computed basis, which kind of get into a little more, but basically I run my program on a number which I already know the prime factors of, and then I use this as my starting configuration when I'm trying to factor n. From this, I don't directly compute the prime factor, but I compute a very small multiple of it, and I'm saying like 5, and it can be used again for another integer, or so I'm hoping. And not to mention, its fractals are very pretty to look at. So first, I'm going to demonstrate how this works in the simplest case using mod 2, which is binary. So I'm just going to zoom in a little bit here. It's my own program. So you can kind of see what's going on here. It's taking the sum of the neighbors. In this case, so we've got 1, 1, 1, 1. So I got 8 neighbors. So this is going to go to 0. And you can kind of see what I mean when you have like fractal tilings here. They're just going to go and go until they collide and then kind of annihilate one another. So this will go forever. Next up, let's try a slightly different configuration. Well, I mean different neighborhood at least. So it's not using this. It's using. It's computing the next state based on the corners right there, right there, right there, right there, and so it's got slightly different different behavior. Mostly, you can kind of. It's what I mean. when I mentioned a diagonal basis in quantum computing is that it's what this is doing is it's dilating along the diagonals of this, and you'll kind of see how that kind of makes a difference soon. But anyways, it's kind of cool. Now what happens if I go mod 3? Well, let's see. Interesting. Let's let it run. And that is neat. What exactly is going on here? Well, if you know anything about fractals, this right here, this is called Sierpinski carpet. And notice how the numbers become partitioned. You get a region of 2s, regions of 1, they all separate out. So this partition is kind of what we're going to be looking for. And you start to see that how it's kind of it's not quite periodic, but it's cycling through and it's creating these, it keeps returning to a self-similar state. Now what happens for something like 12? Let's see. The seizures begin. So this looks kind of noisy at first, but then you start to see how it represents the last two cases, where it was just mod 2 and mod 3, and those turn out to be the prime factors of 12. And so you've got these little these embedded cycles here. They're in a sense fractal complements of one another. So you have groups of 4, groups of 6, so those are multiples of 3, and they're all running kind of next to each other, and so you get these really nice, beautiful patterns. Yeah, let it run for a sec. It's pretty. All right, moving on. So how do we factor n? So if n has a prime factor p, how do we find p? And how do we do this in as few steps as possible? We could check at every iteration and see if our current iteration is the prime factor. If that's the case, most cells are going to go to 0. But this isn't great. You can do this with trial division just as well, and your expected runtime is going to be about the square root of n. You would expect that. Square root of n times square root of n is n. So how do we make the leap over to less than p steps? There are a few things that indicate we can do better. We know that the configuration after a bunch of steps is very sensitive to change, meaning that the structure of the automata is very, very delicate, as I showed earlier. So if you make any changes, it's gonna affect the whole structure. We also see that most cells in the configuration are integer multiples of the prime numbers we're looking for. Unfortunately, they're very big, and we'd still have to factor them. But like I said, how do we make this work for us? We have most of the cells are multiples of what we're looking for, so we need to use this to our advantage. Doing so, if we knew what the multiples were, it would make things much easier, especially if they were really small. So if we compute a configuration with a really small modulus and use that as the initial configuration when we're trying to find n, if we use a really small number like 5 or 7, maybe we only need 5 to 7 iterations before we can check the configuration for p. And that's what I mean, a base in a different basis. So this is, I should have touched on this a little earlier, this is a Moore neighborhood. So the black tiles are just, those are the adjacent cells of a state, and we take the sum of all these cells and reduce them mod some number. You'll also notice that this does expand in a uniform direction. I guess you won't notice it, but it does. Now, for this example, this is the basis that we computed. This took 110 steps, and it's just using 5 times 7. Notice there are 25 little regions in this, and they're all basically copies of, well, there's 5 copies here. The first one being this region, and then the other 4 being here. And I'm going to call these other, these kind of sub-regions, kind of like mixed states, I guess, is the best way to describe them. But they interfered with one another earlier on. But this is good. Now, afterwards, we load our initial configuration, and we compute using mod n and a different neighborhood. I call it the diagonal neighborhood. If you know anything about fractals, this is, I think, a box fractal in terms of a string rewrite. But this is kind of where I borrowed from quantum computing. A quantum register is in superposition if it is in a diagonal basis. So it's kind of a similar result in that it dilates our grid along the diagonals. So let's see how we did here. And I can do this interactively, actually. So for this, that's kind of big numbers. You can kind of see where these lines are going to. This was the initial state in the first cell that generated all of this, and we've got a bunch of points here which correspond to multiples of our prime factors. However, this doesn't really tell us that much because none of them are 0. And that's where we kind of come in, mod 35, which is our basis. And you start to see all of these get mapped to 0. And we have an otherwise very dense region. So it's not that hard to tell where these prime factors are, especially in relation to the center. Anyways, that's more or less the idea behind it. You just keep reducing until you get to a point. This is mod 7, which was after 7 iterations. You can essentially, this is where the idea of sieving comes. You sift out all the extraneous values. These ones got overcomputed, but that's okay. There's still lots of ones. Anyways, another example. Again, this one's kind of a big number. I don't know how many bits that is, like 35 bits or something. But same basis, and it took us 5 iterations to get to this. And you can see again that it lies along the diagonal. So, are we done yet? Well, this was a great proof of concept, but nowhere near being close to done. For the most part, I've been kind of using my own heuristics to choose the parameters, and we need a solid mathematical model to better understand how these parameters change the outcome. The big question is, does this scale with large numbers? And to that I say, I think so, but it's difficult to say with certainty when you're talking about numbers that are well over 100 digits long. So just to summarize, I used Cellular Automata to factor an integer n by pre-computing with some smaller basis, and then iterate a few times, and then I get a really small multiple of the prime factor I'm looking for. And this turns out to be kind of similar to how the general number field sieve works, but I'm optimistic that I can do better. Anyways, any questions, comments, insights, feel free to email me. I really enjoyed doing this. I'm sorry I went 5 minutes over, I think. Again, thanks for watching.